Let's start with question number 19. Now in this question you can see this belongs to chapter gravitation, again a part of mechanics. A satellite is moving with a constant speed v in circular orbit around the earth, right? The object of mass m is ejected from the satellite such that it escapes the gravitational pull of the earth. At the time of ejection, the kinetic energy of the object is. So let's start with the solution. As you are aware that potential energy of the object is always twice the kinetic energy for this satellite which is revolving. So you will say u is equals to minus 2 into half m v square, because along with the satellite that object was initially revolving around the earth. Now with this you will have minus m v square as the potential energy, right? Now in order to escape the gravitational pull of earth, the total energy of the particle should be 0. That means potential energy plus the kinetic energy at that moment of ejection should be total be 0. In that case, k would be equal to minus of u, that would be mv square. So let's see which is the best suited option here. Among the 4 options, option number 2 would be the right answer for this question, right? Let's move ahead for next question, that is question number 20. Now this question belongs to electrostatics, that is the section of electromagnetism. A charge q is distributed over 3 concentric spherical shells of radii a, b and c such that their surface charge densities are equal to one another. That is, sigma for all the 3 spheres would be same. The total potential at point at a distance r from their common center where r is less than a would be. That means there are 3 concentric spheres and inside the smallest sphere there is a point which we have to find the potential. And you must be remembering that inside the hollow sphere the potential at each and every point is same. That means if you find the potential at the center of the concentric circle, that will be answer for this case as well. So let's start with the solution. First of all, individual charges q1 would be 4 pi a square sigma, q2 would be 4 pi b square sigma and q3 would be 4 pi c square sigma. Now the summation of these 3 will be the charge, that is q1 plus q2 plus q3. Solving this you will get 4 pi sigma is equals to a square plus b square plus c square, that is equals to q. This is the first equation. Now when you talk about the potential at the centroid, potential would be k q1 by a plus k q2 by b plus k q3 by c. Taking k or 1 upon 4 pi epsilon naught as common, you will get, instead of q1 you may write 4 pi a square sigma by a plus 4 pi b square sigma by b plus 4 pi c square sigma by c, right? Solving this, 4 pi and 4 pi will be cancelled. What is left would be sigma by epsilon naught a plus b plus c. This is the potential. Now we need everything in terms of q. So we have a relation with us between q and sigma which we have derived right here, that sigma can be written as q upon 4 pi a square plus b square plus c square. So let's write it down here. So v would be equal to 1 by epsilon naught into, instead of sigma I can write q upon 4 pi a square plus b square plus c square, and this should be multiplied with this remaining a plus b plus c. Thus, this is our answer for the potential. Let's see which is the best suited option here. So, as per our solution, option 1 is the best suited answer for this question, right? Let's move ahead for our next question. Now, this question belongs to segment of electromagnetism again. Here, there is a charge insulating rod which is rotating with a speed, that is n rotations per second, and the linear charge density is given to us as this. Now what we want to find is the rod makes n rotations per second, then the time average magnetic moment of this rod is required, right? Let's start with the solution. So let us first assume a rod-like structure like this, right? This being the origin, it is being pivoted here, and charge is distributed uniformly along its length. It is rotating with a frequency n, that is the n rotations per second. If I take a particular segment, a very small segment of thickness dx at a distance x from its pivot point, so it will cover some area, as you can see, a circular area of pi x square in a given time. Now, if you want to find the magnetic moment, the small magnetic moment, let's take, it would be I into A, that is the area of the coil or area of the rotational circle. So that would be dq into n, that is the rotation, into pi x square, right? Now, if you want to find dq, it would be simply rho into dx pi x square. Now, what can you write in place of rho? You can write rho naught x by L into dx into n into pi x square. This is the magnetic moment of this integral portion. Let's integrate it 0 to m, and this integration should be 0 to L. Solving this, rho naught by L, n pi will be constant, they will come out. What is left is x cube dx integral from 0 to L, right? On solving this one, you will get rho naught n pi by L, L to power 4 by 4, right? Thus solving this, you will get 1 by 4 rho naught n pi L cube. This is the magnetic moment of this rotating rod. Let's see which is the best suitable option for same. So among these 4 options, option number 3 is the answer to this question, right? Let's move ahead with our next question, that is question number 22.